if t is a linear transformation from v to w, and we look at all of the elements that in w that t mapped something in v to, that is the range of t, that might or might not be the whole space w. If it is the whole space w, we call the linear map surjective. Let's look a little bit at that property. Suppose V and W are vector spaces. And let's consider some element little w in the vector space big W. For some linear maps, T from V to W, there might be an element little v in big V such that T of little v equals little w. For other maps, we might have T of v is never equal to w. So there's no rule about linear maps. That says we have to actually hit all elements of W with elements of V. So for example, let's let Vk again be polynomials of degree less than or equal to k. And let's let t of 1 from v3 to v2 map p of x to its derivative. Now if a0 plus a1x plus a2x squared is an element of v2, then the element, let's say q of x in v3, which is a0x plus a1 over 2x squared plus a2 over 3x cubed, satisfies t of q equals derivative of q, which is a0 plus derivative of a1 over 2x squared. We'll bring down the 2 and we'll get 2 over 2a1, which is just a1. And then here we bring down the 3 and get 3 over 3a2, which is just a2. So no matter what element we pick in v2, there's something in v3 so that t of that something equals our original element of v2. We can hit this polynomial in v2 if we start with the appropriate element of v3. Now let's look at another transformation. Now define t2 from v2 to v3 by sending every polynomial to x times that polynomial. Now we have the one polynomial in V3, but no polynomial p of x in V2 satisfies T2 of px equals 1, i.e. x times p of x equals 1. P of x would have to be 1 over x, but 1 over x is not a polynomial. There's no polynomial of degree less than or equal to 2 such that x times the polynomial equals 1. We call a map T from V to W surjective we can say this in a couple different ways. Or we say T maps V onto W. Or say T is onto, if you don't mind using a preposition as an adjective. I mind, so I'm never going to say T is onto. Some people say that. The book says that, so I'll mention it, but I'm never going to say it again. So we say any one of these things if the range of T of capital V, is all of W. So we don't miss anything. In this second example, we missed the element 1. There's no polynomial that we can apply T2 to get 1. So the range of T2 is not all of V3. Now there's a coordinate version of this. Suppose we fix bases B and C of V and W. Let's let A be the matrix of T with respect to B and C. Then T is surjective, or T maps V onto W, or those two options, if, oh, I guess I need a dimension for W. So let's say fixed bases B and C of V and W, and let's let the dimensions of V and W be N and M. And A is an M by N matrix. And T is surjective if and only if the column space of A is all of Rm. So our M is the coordinate version of W. So if all possible linear combinations of the columns of A equals all of our M, that means that we're getting everything in Rm. Every coordinate vector of an element in W is a linear combination of the columns of A. So this is the same as hitting every element in W with the linear transformation. Left multiplying by A, a vector X is like taking a linear combination of the columns of A. The end.